In a traditional x86 desktop computer, you only have one processor, or CPU, and only usually one GPU, or graphics processor. That CPU may have any number of cores, hyperthreading, and a fast clock speed, as I covered in my recent video breaking down CPU performance metrics. But that's still just one CPU. What happens when a device has multiple different processing units at once? In this video sponsored by ARM, we're going to explore just that. I referenced two different ARM-based processors powering the flagship smartphone in that CPU performance video, and that confused some people. The concept used to confuse me too. I'm used to desktop systems with only one processor, or at the very least, a more server-oriented system with multiple identical processors. But in the era of AI, where more efficient AI compute is required to deliver capabilities, ARM does things differently. Smartphones, tablets, vehicles, and IoT devices are often computing using a SoC, or System on a Chip design, wherein multiple processing chips are working together to run your system and complete tasks as efficiently as possible. This is done through the workload concept called heterogeneous compute. Heterogeneous compute does technically still apply to traditional systems too, wherein your desktop is able to play a video game or edit a video by using a combination of the CPU and GPU cores for graphics. Heterogeneous compute has revolutionized workloads such as video editing or research even in recent years by leveraging the widespread gaming graphics cards alongside processor cores to speed up tasks. In editing, like in DaVinci Resolve for example, video decoding, effects processing, video encoding, and audio processing is balanced between the CPU and the GPU based on which hardware is best to optimize for the given task to drastically speed up production compared to CPU-dependent editing bays of years past. But in an SoC system, like a smartphone, you will often see two different kinds of CPUs. For traditional instructions, a GPU for graphics and 3D workflows, a NPU or neural processing unit for AI-related tasks, and possibly even more niche specialized chips like an ASIC or FPGA for that kind of stuff, plus hardware to control I/O ports and capabilities. Since these devices are closed platforms, meaning the user isn't changing individual components and introducing unknown variables or combinations to the mix, the software can be optimized to take advantage of the entire set of hardware to perform its best. Heterogeneous compute enables a single system to have multiple computing subsystems that either work independently or in parallel on a task. A smartphone with a high-power CPU and a more energy-efficient CPU may prioritize short burst actions, like taking and processing a photograph or video clip on the high-power CPU, but optimize longer session work, like video streaming, to the more energy-efficient CPU to extend battery life. For mobile, the ARM Compute Subsystems for Client features the ARM v9.2 CPU cluster with the ARM Immortalis G925 GPU I mentioned before, that accelerates various AI use cases such as image segmentation, object detection, natural language processing, and speech to text. And the Vivo X200 smartphone, for example, the MediaTek Dimensity 9400 SoC features that ARM v9.2 cluster I mentioned, consisting of one Cortex X925, 3 Cortex X4, and 4 Cortex A720 CPU cores, plus the Immortalis G925 GPU. It's a lot. This provides massively accelerated gaming and AI performance, including AI render upscaling to improve game performance even more on the fly. By leveraging a cluster of different processing units optimized in different ways, heterogeneous computing assigns tasks and balances workloads in a way that can provide the best performance and be as efficient as possible, especially important in battery-powered devices like smartphones and tablets. In the cloud, the Grace Blackwell Superchip combines NVIDIA's Blackwell GPU architecture with the ARM Neoverse-based Grace CPU. The design optimizations that have come from this have reduced energy consumption by 25% and provided a 30x increase in performance per GPU compared to the NVIDIA H100 GPUs on their own. That's a lot of horsepower and some serious shrinkage in hardware required for it. The flexibility of the ARM Neoverse platform allowed NVIDIA to implement their own high-bandwidth NVLink interconnect tech, which you may recognize from running multiple GPUs in a consumer desktop system, but in these cloud systems allows massive improvements in data bandwidth and latency between CPU, GPU, and memory. In IoT, the ARM Ethos U85 NPU runs with Cortex-A-based systems to accelerate AI performance, such as factory automation on edge devices. The Cortex A320 is the smallest ARM v9 implementation, featuring over 50% efficiency improvements compared to the prior Cortex A520. The Cortex A320 also delivers 10 times machine learning processing uplift compared to its predecessor. These continued optimizations in hardware combined with software that can seamlessly leverage multiple CPUs, GPUs, and NPUs provide massive innovations in processing of normal workflow tasks and AI processing on ARM platforms. This is why I kind of wanted to get back to basics a little bit, as it were, this year with teaching this stuff. As I have previously talked about how Moore's Law is slowing down with regards to scaling compute performance of hardware. Components just don't keep scaling up anymore. We need to leverage them in more creative ways, and ARM is leading the charge in innovating these platforms by leveraging optimized hardware to scale performance and maintain battery life or power efficiency, which ultimately just means better quality streams, better looking games, and nicer looking photos for you on your device. If you want to learn about all of this, I recommend checking out this report ARM released this month with MIT Technology Review called The Future of AI Processing. I'll have a link to it in the video description. Check this video to learn how all of these optimizations improve services you use every day, such as YouTube, that you're likely watching this video on right now. And remember to be kind, rewind.